Okay, up to this point, all we have done in terms of considering the magnetic flux that's associated with the DC generator is in reference to the poles. And, we talked about the north-south pole, and the two-pole generator, and we were looking at different things. And then we looked at a six-pole in an example. And, the poles of the generator supply the flux that, creates the voltage as the conductors are cut across that. Now, something else that we have to think about when we're talking about a DC generator and other electrical machines is that once current starts to flow through these coils, through these conductors, when we connect a load to them, then any current carrying conductor also has a magnetic field associated with it. So now what we have the magnetic poles of the generator, and also we have a magnetic field that's associated with the conductors. So those two magnetic fields interact, and the effect can be such that it weakens or distorts the primary magnetic field from the generator generator poles. And there's certain bad things in terms of the efficiency and the output of the generator. And the whole area in general is section 4.9 in chapter 4, and it's called armature reaction. So let's look at that in some detail and see if we can understand what's going on there and see what we can do to alleviate the effects from that. So figure 414 is showing the magnetic field that's produced by the current that's flowing through the armature conductors when we connect a load to the DC generator. A couple of things to observe when we're looking at that. First off, these magnetic flux patterns and the magnetic flux in general, it operates at right angles to the actual generator poles, the magnetic field supplied by that. So it's opposite. I mean, it's not opposite, but it's acting against the poles that are producing magnetic flux. So the other thing too that he mentions here is that although let's say this is a north and this is a south pole and a two-pole generator, the other thing that he mentions here is that this flux, it's variable, and it's variable based upon the amount of current that is flowing in the armature conductors. You have more current, the flux is going to be greater. And so, even though the pole flux that's generated, say, from the north and the south pole is constant in most cases, the armature flux, which is what we call this, the armature flux is the magnetic flux generated by current flowing through the armature conductors, it's variable. And so it changes. It's not constant, but it varies with the load. So this armature flux, there's two primary problems that occur. The first one we can look at here is, when we're thinking about the neutral plane and all in the earlier sections, notice now that there is flux in this neutral zone. And we know that if there is flux in the neutral zone, that will generate a voltage across the coil that is in that neutral zone. And if we have that situation and we go and the brushes are shorting out the commutator segments for a particular coil, say this was you know, a coil and it's in this position, and normally we would hope that there would not be any flux, but you know, now there is. We get this situation that we try to avoid, to where current is flowing in the coil when it's in what should be the neutral position. That's a problem. Arcing, sparking, all that sort of thing that we talked about earlier occurs. The other problem that this armature flux causes is a distortion of the fields that are produced by the north and south pole. It no longer looks like it did originally, and that causes additional issues for us. And what basically happens there is that this neutral zone gets shifted. And we saw an example earlier why, you know, how that causes all sorts of issues. And so, you know, he mentioned specifically in this case, the neutral zones have shifted in the direction of rotation of the armature. They've shifted in the direction of rotation. So that's a common occurrence in a DC generator. And it's something that we need to figure out a way to prevent that from happening. One other final effect that he mentions is that the flux distortion that occurs causes some problems in the pole tips themselves. And if you look, you know, in the pole tips, there's a saturation that occurs. He says that the flux density in pole tips 2 and 3, and I've covered these up, haven't I? He says the flux density in pole tips 2 and 3 causes saturation. Consequently, the influx in under pole tips is less than the decrease in flux under 1 and 4. As a result, the total flux produced by the north and south poles is less than it was when the generator was running at no load. This gives us a reduction in the induced voltage that we would, you know, look at from equation 4.1. And again, equation 4.1 was written, you know, with the idea that, you know, this neutral zone was in the position that we said it should be. This occurrence, this armature reaction occurrence and all, he says that the decrease in flux for a very large generator could be as much as 10%. And so, you know, we have to figure out a way or include something in our design that can help alleviate that. And we'll look at some possibilities for that in the next two sections.